So, as we are doing rotational dynamics, so we will be dealing with the rotational force. Okay. So, as we know that in linear motion, we have force is equals to mass into acceleration. So here in rotational motion about a fixed axis, we have torque. So torque is equals to R cross F, and there will be like as analogy, we'll have one more formula, that is torque is equals to for M we will study moment of inertia I and into alpha. So we will have here two formulas of torque. One is the analogy of this formula, like F is equals to Ma, and the second one, torque is equals to R cross F, which is the prominent formula. Okay. Now, if we see, we have figure in NCERT book also. If you would like to see, this is a very typical figure actually. Let us understand this figure. What this figure is. So, let me take this figure. Let me draw it. Run down. So, students, suppose I have a nut over here. And I want to open this nut with wrench. Yes. So this is my wrench. I want to open this nut. So I will apply the force from the hand. I will hold this wrench. How I will holding it? Actually I should hold it, to apply the maximum force. I should hold it at 90 degree. Okay. So so this is your R. This is your R vector. If this is origin, this, because this is the axis of rotation, right? So this axis of rotation, so let us call this origin. So axis of rotation is it's perpendicular to the plane of the board, right? So this will be your direction of this is your R, that's your R, and that's your F. So that's how you open this nut. Okay, agreed? So apply the force here and this rotational force. And what is the direction of torque? R cross F. It is further perpendicular to the plane of R and F. Okay. So put your fingers. So this is your R. I told you this is your R. Direction of R. And this is your F. So put your fingers on R and curl them towards F. So tell me, students, what is the direction of torque? What is the direction of torque? Yes?
Outwards.
Yes, coming out of the plane of the paper. Very good. So coming out of the plane of the paper. So put your fingers on R, right hand side, right hand fingers on R. Yes, on R, and move them towards F. Okay. So from R to F. So your thumb will point out of the plane of the paper. Have you got this, students? I hope you have understood this. Now the question is that, so here the torque is equals to R cross F, and that's equals to RF. So that's the magnitude. If I'm writing only magnitude, this is RF sine theta. That's my only magnitude. I will remove this vector sign, so only magnitude. And further, I can write this magnitude as, see, if we look at one more figure, suppose this is your R, and instead of applying force at 90 degree, suppose now I'm applying the force. So this is your direction of R, right? I'm applying the force F. Okay. Here the theta was 90 degree. Okay. So here the theta was 90 degree. This was your vector R, means the direction of vector R. Okay. So here the angle was 90 degree, direction of R and F. But here the angle is not 90 degree. Okay. So this is the figure which is there in our book. This figure is there in our book. So that's figure 7.18. So now I hope you have understood this figure. Okay. So nut is there, suppose, but here I am not applying the force at 90 degree with the position vector, but I am applying the force at a certain angle. So this is not a good way to apply the force. You will get less torque, because lesser theta means that theta lesser than 90 degree, the torque will be lesser. Okay. Now this angle is theta. Okay. So now I need RF sine theta. So sine theta can be along with R or can be along with F. So if you are taking it along with, suppose, R, so if you draw, so I want to show you the figure that is drawn in your book. See, students, very important thing. Where is your R? Where is your R here? This is the direction of R. Where is your R here? Where is the, see, this length is F. Okay, very important concept, very important. This length is the magnitude F. Okay, this F vector, this is its magnitude. This is R vector. This is your R vector. So you need to write arrow over here. This is your origin. So this is R vector. This vector R. And what is the length? This is your R. This is your R. I hope you people have understood it. Okay. So this is not the case like this is your A, this is your B, and you are drawing perpendicular from B on A. Okay. And this is your B cos theta, B sin theta. And if you are finding A cross B, then it will be AB sin theta. Okay. And means the direction with the cap. So here this is means this length of vector A from here to here, this whole length vector A, and into the, you know, we can also write it as A into perpendicular component of B. This is another way of writing this. Okay, this is very important, students. So what is the magnitude of A cross B? So magnitude of A cross B is magnitude of this length of vector A into perpendicular component of vector B. So B perpendicular, this length. Now let us see here. So here the formula will be tau is equals to, we can write it as F into R sine theta, and tau is equals to F into R perpendicular. Okay, got it? So this R sine theta is perpendicular on F. Now here in this case, how shall we draw the perpendicular on F? So how we are going to take it? So obviously what we are going to draw, I need to further extend this force, right? And this angle will also be theta. So vertically opposite angles, this angle is also theta, right? Now draw a perpendicular on this line. So this is your perpendicular. Okay, got it? So this is your line. Now what is R sine theta? So opposite side, opposite is equals to hypotenuse sine theta. So this theta, this is opposite side, this is your 90 degree, opposite is hypotenuse. So this is hypotenuse sine theta. So this side, okay, opposite side. So opposite side is equals to hypotenuse sine theta. And what is your opposite side? This distance. So this distance is equals to hypotenuse R sine theta. So this distance is, this length is your R perpendicular. So R perpendicular here is R sine theta. So this is your length R sine theta. This is your length R sine theta, and this is your length F. So you are multiplying this F with R sine theta. So so this was a very simple diagram, but this is a little bit typical. Okay. So you need to extend the F here in this case. So students, I hope you have understood the figure which is there in your book. Okay. What about, sir, in this case? In this case, this is your line of action. What do we call it? What do we call this line? Where the force is applied?
Line of action.
Yes, very good. This is what we call line of action. So you have to, from the axis of rotation, this is your axis of rotation, taking as origin. So from origin you have to draw perpendicular on the line of action. This is what you need to do. So here, this was your origin. So draw, so this is your line of action. So draw the perpendicular from here on the line of action. So this is the same length. This is your R perpendicular here. So here R perpendicular is equals to R, because R sine theta, and theta is equals to 90 degrees, so that is equals to R. So your R perpendicular and R were same. So this is what you need to do to understand this concept. So it's so easy. Okay. So draw the line of action, and from the axis of rotation draw a perpendicular on it. So you'll get the perpendicular distance of R. See, this is your line of action. Okay. So what is the shortest distance from the axis of rotation and line of action? So this is also a distance, but this is the shortest distance. So the distance between axis of rotation and line of action. Okay, so that is your r sine theta. So you need to take the perpendicular distance. See, this is also a distance O, and this is suppose point P. So OP is also the distance between line of action and origin, but this is not the perpendicular distance. This is the perpendicular distance, which is your O. You can name it any point, like OT you can name. Okay, so OT is your perpendicular distance. So this is your OT. So OT is your perpendicular distance. So this is what you need to take in the top formula. So students, always find the magnitude and then you know the direction. Put your fingers on R and curl them towards F. Direction will always be perpendicular. So doesn't matter what your theta is. So that's the key point. So this all direction V, tau and L, the direction will be perpendicular to the plane of these two vectors forming the cross product. So this direction does not depend on angle theta. Direction will always be perpendicular to the plane containing R and F. So put your fingers on R, curl them towards F. Your thumb will tell you the direction of the cross product. So simple, students. Got it? This figure which is there in your book? Yes? Yes or no?
Yes, sir.
Okay. But students, let me tell you, today's class is one of the most important classes, because to understand this figure and this concept, see, is means now you are understanding it clearly, because we do it, but we know this formula also, but not actually understand the concept behind it. Okay, now let us see here this slide. A net external force causes linear motion to change, because translational motion along a curved line, which is curvilinear motion or linear motion. Now look here, this boy, actually this is not this means this jump is this. So this is a pure translational motion, because all the points on the body travel on the parallel path. So this parallel path need not to be a straight line, but these paths you can see, this curve, this curve, this curve. So these three curves are parallel. Now let us see the combined translation and rotational motion. So look at look here. So he is so this motion is so translational as well as rotational. So we have these figures in our book also. If you look into your NCERT book, this is figure 7.6a and this is figure 7.6b. Okay, so in that you were throwing a sort of bottle. Okay, so in rotational means rotational motion, one point here, this one point is fixed. So this is your this path is the path of center of mass of the body. Okay, yes. Now see, let us complete this. For simplicity, the force lies in a plane perpendicular to the axis of rotation. So this is the case that we are taking. Force lies perpendicular to the axis of rotation. Okay, so the axis of rotation is perpendicular to this page and the force lies in the plane of the paper. The line of action is extended line drawn collinear with the force. So this is your line of action. Collinear means they are along, means the same line. the lever arm is the distance L between the line of action and axis of rotation. So this is your axis of rotation. This is your axis of rotation here. Okay, at O. So axis of rotation at O, passing through O, the axis of rotation passing through O. Passing through O, okay, this point. And now you need to have the distance between the line of action and the axis of rotation, and that is a perpendicular distance. So here the force was, this was your line of action, and this is the axis of rotation. So you will take this vector R for R cross F, but for magnitude you are taking the perpendicular distance, this perpendicular distance. Okay, so you need this R for the direction only. Okay, this and this R sine theta is a perpendicular distance between the line of the action and this. So tau is equals to F R perpendicular. So this R is perpendicular on the line of action, which is your line of action, means the which is collinear with the force. Okay, so how will you be writing the magnitude of torque? So here he is writing L instead of R. So tau is equals to F into R perpendicular. This R perpendicular we also call it, yes, in physics, this R perpendicular we call it, what do we call it? Lever arm. What do we call it? Lever arm. This is important, students. We call it lever arm. Okay, so tau is positive or negative. So you know that this is a reference line, and if you move in the anti-clockwise direction, then your theta will be positive. Okay, and if you move in clockwise direction, then your theta will be positive. So here also, in which direction you are moving here? This is R and F. So R cross F, you are moving in which direction? Positive direction. So tau will be positive. So tau is positive here. Is this clear, students? So positive tau. If this is your R, this is your F, so you are moving from R to F, you will get positive tau. Students, you will only get attendance when you will say yes. Software will only record the attendance. It is sensitive. Is this clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. Now, and tau will be negative. In this case, if you have the F here and you need to move your hand from R to F, so here the tau will be negative. So tau is perpendicular to the plane of R and F, and it can be positive if you are moving your fingers from R to F and thumb is pointing outwards. But in this case, what is the direction? If we are considering this R and this F, what will be the direction of the torque? Inward, right? Negative z-axis, you can say. So this positive z-axis coming out. So put your fingers on this R and move towards F. Yes. So where is the thumb pointing? Thumb is pointing into the plane of the paper. Okay, that's negative tau. And what are the units of tau? What are the units of force? Newton. And what are the units of position vector? Distance. That is your
Meter.
meter. Okay, so Newton meter. Now this is your door, students. This is your door. So this is the top view. Which view is it? Top view. You are looking at the top, from the top. This is your door, okay? Not exactly a top view, nearly top view, okay? Because top view you will see only the rectangle, okay? But here you can see the door also, so at a certain angle. So you are from the top, you are watching the door, and it is easier to open the door if you apply the force in the 90-degree direction, okay? And this is your axis of rotation. So door is easier to open because tau is, so here the angle is 90 degree, so maximum torque is applied. So this is the means you can say this figure is what do you call this figure? We have drawn it. Yes. What do you call these kind of figures?
Free body diagram.
Yes, very good. This is free body diagram. So this is your free body diagram, sort of. So this is your axis of rotation. This is your force. So force, this is your line of action, okay? This is your line of action. And where is your R perpendicular? So draw a perpendicular from axis of rotation to the force. So this length is your R perpendicular. So R perpendicular and R is same. So this is just like this example, okay? This figure and this figure is the same. Now what about if you are pushing closer to the axis of rotation? Does it increase your lever arm or does it decrease your lever arm? Decrease. So suppose here the tau I am getting was tau 1, this magnitude, and here I get the magnitude tau 2, okay, in this figure. Now I am applying, so either I am changing the R. So which one is greater, tau 1 or tau 2?
Tau 1.
Tau 1 is greater, yes. So tau 1 is greater than tau 2. This is tau 1, so tau 1 is greater than tau 2. Now there is third figure. Now this force, so you are not applying the force at 90 degree, but you are applying the force with some acute angle, okay? So here you are applying the force. So here you were applying the force at 90 degree, right? But this figure belongs to this figure, okay? This figure this is the free body diagram of this figure, okay? So now look at this figure. You are applying the force at some angle, not at 90 degree. Like in this, you are applying the force at 90 degree, but here you are not applying the force at 90 degree. So this is your line of action now, yes? And this is your axis of rotation, right? So axis of rotation, draw a perpendicular on this. So this was your R, this was your this was your R, okay? And this is your this is your R perpendicular. So this angle is your theta. Don't get it confused, student. This is your R, okay, and this is your F. So the angle between R and F, so this angle was, this is the angle here. So this is the angle that you have got. So which angle is it? So this angle you are considering it as theta. So this is theta, this obtuse angle here. So which angle, what angle will I get here?
180 minus theta.
180 minus theta. Okay. So this theta is totally separate thing here. The important thing is that this is the axis of rotation over here at this point, and this is my line of action. So simply I need to draw so this is your hypotenuse. So this will always be your hypotenuse. This R will always be your hypotenuse, and this will always be the opposite side. So opposite side is equals to hypotenuse sine theta. So as here your theta will be actually 180 minus theta, so here this will comes out to be opposite side, which is this L, or you can write it as R perpendicular, is equals to hypotenuse or R, and this sine 180 minus theta will be your cos theta. Okay, got this concept, students, for this figure? Yes, because here this angle that you are taking is 180 minus theta, so sine 180 minus theta is cos theta. So this is the perpendicular length, or you can say lever arm, always. Okay, got it?
Yes, sir.
Now this is your line of action. This is so this is supposed tau 3, the force which is applied here. So tell me which one is greater, tau 1 or tau 3?
Tau 1.
Tau 1, very good. So tau 1, the magnitude of tau 1 was greater than the magnitude of tau 3. Okay. Students, remove the vector sign over here because you are comparing the magnitude only. So tau 3 is lesser, here also tau. So tau reduces if you reduce R, or if you decrease the either increase or decrease the angle in both the cases, because you know that the sine function, if you draw, this is your theta, this is your sine theta, this graph, this is your plus 1 and this is your minus 1. Okay, so these are the maximum and minimum values of sine theta. So sine 0 is 0, right? So your graph starts from here and it reaches maximum at pi by 2. So the graph reaches maximum at pi by 2, and then again it becomes 0. So the value of sine is maximum at 90 degree. So it is lesser than 1 if the angle is between 0 and 90, and always and further lesser than 1 if the angle is between 90 and 180. So it is maximum at, so the torque is maximum at 90. If you increase or decrease the angle, means if you are taking acute angle, like in this case it was acute, and here the angle was obtuse. So either taking acute angle or obtuse angle, in both the cases sine theta will decrease. So sine theta will decrease, so the torque will decrease. Got it, students? And now let us take this figure. So this figure, actually you are applying the force towards the axis of rotation. Okay, so this is your axis of rotation and this is your line of action. So what is the angle here? What is theta here in this case? Yes,
0.
0. Yes, so theta is 0, so tau is equals to 0. So now apply the force in this direction. Open the door and apply the force. Will the door move? Will the door move?
No.
No. Students,
No, sir.
students, I want you to do these 3 cases. Go near to the door and try these 3 cases. Okay, I am just giving you 1 minute. Go to the door, apply the force in this direction, and then change the direction. Apply the force in this direction. Okay, so reduce this angle. Okay, you will find that it is less torque is applied and it is a little bit difficult to open the door. And if you apply the force here near to the axis of the rotation, you will see that it is difficult to move the door. And then you apply the force along in the direction of axis of rotation. So you will find that here the students, sorry, one thing, if the theta is 0, then also torque is 0, but in this case actually theta is R and F. Yes, what is the angle between R and F? Yes. What is your R perpendicular here? First of all, what is your R perpendicular here? The distance between the line of action. This is your line of action, this is your line of action here, this is your line of action, and this point. So the point actually lies, the axis of rotation is on the F. So R perpendicular is 0 here, first of all. So why r perpendicular is 0? So theta is 0 because, okay, because r sine theta and theta is 0. So r sine 0 is 0. Okay, so that's how we can understand it in terms of theta. And what is r here? What is r here? So theta is 0. What is r here? This is your, this distance is your r. So r is not 0. Okay, we have the r. R is okay. So this is my vector. This is how we write r. Yes, this is how we write r. So r perpendicular is 0 here. Okay, because the theta is 0. So sine theta is 0. So you can see that, is it 0 or is it 180 degree? Is it 0 or is it 180? Yes, students? Is it 0 or 180? This is the direction of r. We need not to get confused. So this is the direction of r from the axis of rotation to the point where we are applying the force. So this is the point where we are applying the force. So this is r vector. So this is the direction of r vector, isn't it? So here the angle is not 0 degree. Here the angle is 180 degree. What is the angle here? 180 degree, isn't it? Sine 180 is also 0. Students, understood this concept?
Yes, sir.
Your r is in this direction. Okay, so you are unable to apply the force in this direction, but if you apply the force in this direction, then only the angle will be 0 when r and f are in the same direction. But here you can clearly see that the r is in this direction. Okay, so this is the direction of r. Direction of r is the position vector. Position where you are, the point where you are applying the force. So this is the point where you are applying the force. This is the point where you are applying the force, and this is the axis of rotation. So from this point to this point, draw the position vector. So that's the direction of r, and you are applying the force in towards this direction. Okay, so here the angle is here the theta is 180 degree. So theta is 180 degree here, and your r perpendicular, which is your r sine theta, that is r sine 180 degree. So sine 180 degree, this sine 180 degree is also 0. Okay, got it?
Yes, sir.
Students,
Yes, sir.
So write it down and do this with your door, applying the force over here. So what affects this tau is equals to, you know, r sine theta. So if you reduce the force, tau will be reduced. If you reduce r, here you have reduced r actually. In this case you have reduced the r, and the next case is you are reducing, increasing or decreasing this angle theta. Okay, theta becoming lesser than 90 or more than 90. So like in this case, theta was greater than 90 degree. So then also this torque will reduce, and when this theta will be when this will be, the angle between f and r will be 0 or 180, then the tau will be 0. Okay, so this is very, very important point, students. Okay, I hope you have understood it clearly.
Yes, sir.
Noted it down. Shall we move forward? Yes. So tau is 0 if either r is 0 or f is 0 or theta is equals to 180 degree, 0 and 180 degree. So students, you can read your NCERT book now, topic 7.7.1 from your book. So what we have done is topic 7.7.1 your NCERT, and which is your page number 154. Okay, so this is what you need to now just give a reading in your book of this topic. Okay, now shall we move forward?
Yes, sir. Yes, sir.
Okay, thank you. Now the next slide is equilibrium. We'll do it in some other class, but now let us understand this talk. Let us do one see Karthik asked me a question. So students, this is simple a rod. Okay, you can consider it as rod or plastic pipe or rod, whatever you say, you have this. Okay, so it can be any plastic pipe or a rod. Now you have a bag, and you are hanging your bag. All of you have your school bags, no? Yes, very fancy type school bags you have. So this is your bag that you have, and you are hanging it over here. Okay, and you are holding this bag from your hand from this. So this is your hand, and you might be holding it from both the hands, or you might be holding it over here. Okay, now if your bag remains in this position, and you are holding it, this pipe from here. Student, this is very good thing. Means I'm not that good in drawing. So you are holding it from here. This is your hand holding. So hand, okay, holding it from here. So you will see students, here it was in equilibrium. So that's also our next topic. Equilibrium means no change in state, no change in position. There is no change in position. Okay, that's equilibrium. So why there was no change in the position of the bag? Why the bag was not moving here in this case? Yes, why the bag was not moving? Why the nothing was moving? Yes, tell me.
Opposite forces applied by the hand.
Yes.
The guide.
Okay, good. So if I draw free body diagram, this is the center of mass of the bag. So what is the force applied on the center of the mass? Downward force, that is gravitational force, Fg, that is equals to mg, and this is the same exactly upward force you are applying, right, in the upward direction, right? This is your force in the upward. So upward force was equals to downward force. Okay, so F is equals to, which is your upward force, is equals to Fg, which is your downward force. So it was not moving. So if your hand was pulling it, it was pulling your hand. Okay, you can say it. So Newton's third law. Okay, and you can say these forces are equal because acceleration is 0. So net force applied on this bag is 0. F external is 0. So that is your Newton's second law. And if there is no change in the state of the body, then F external is 0. So here, because A was 0, so that's your Newton's second law, and there is no change in state, so that is Newton's third law. So all the laws, you can. So if the force with which your hand is pulling the bag, same force, your bag is also pulling your hand, same gravitational force is there. So that's equilibrium. But here, what you have changed the position of your hand now. Okay, and what you will see. So here, suppose you were applying. So here, suppose the forces were 10 Newton. Okay. The mass of the M was equals to 1 kg. Okay, M is equals to 1 kg. So the force was 10 Newton. Now, here, this, if you are still applying the same 10 Newton force, this rod will, or this plastic pipe will bend, and this, you can do this, okay? You might have a plastic pipe at home and put your bag. So your bag will move down in this direction. But see, the important thing is that, okay, this is a translation motion. But you can see this rod, this has become your axis of rotation. And this bag and these rods, they are both moving in this direction. So that's your rotational direction. That's your translation motion. So, and that's your rotational motion. So rotational motion can only be there. So here it was equilibrium because here F was 0 and tau was also 0. So that's the condition for equilibrium. For if you want linear equilibrium, so linear equilibrium where F is equals to 0. And torque is equals to 0, then there is rotational equilibrium. There is no rotational motion. Rotational equilibrium. Okay? Rotational equilibrium. So here, it means if it is rotating, if this is the axis of rotation and this this plastic pipe is rotating, and this bag is, of course, it is rotating, coming down this way, along with translational motion. So it means that the tau is not equals to 0. So what is your if you are where is the action of force? So this is the center of mass. Suppose this is the action of force. So and means line of action. Okay. And line of action is changing, means tangential to it, to this. So, and this will be your means this is your R. So what is the difference between this case and this case? Here, your F and means it was not rotating because if you rotate it, then this is your axis of rotation will be over here. Your hand is over here. You are applying the force over here. So in this case, students, R is equals to 0 because, or okay, or if see means what do you see? Means what do you say? Here, what is so here in this case there is no R. So, but here in this case, this is the axis of rotation. This is your R, and it is rotating because of the tau. So tau is not equals to 0 here. So tau is equals to F into R perpendicular. So where is the line of action of force? Suppose this is your line of action of force, this direction, this line of action of force, and this is your direction of R. So isn't it? This will be your direction of R. So the same case as we did here, the angle between R and F, obtuse angle, and this. So what is the perpendicular distance? So this is your axis of rotation, this is your direction of force. So from means line of action, this line of action. So from axis of rotation, draw a perpendicular, because I want the perpendicular distance between the axis of rotation and the line of action. So this is your 90 degree. So this is your R perpendicular. So you know F, you know R perpendicular. This is your lever arm, or this is your R sine theta, this length. Means if this is theta, if you are considering this as theta, then only it is sine theta. If you are considering this as theta, then this will become your R cos theta, because this will be this is theta, this is 180 minus theta. Okay, like we did earlier. Got it?
Yes, sir.
So here the theta that you take is actually this one. This is your theta. Okay. So here there will be rotational motion. So here the torque was 0, but as you increase this R, now hold your bag here. Instead of, so this is case 1, this is case 2, and in case 3, I am holding the bag. Now the bag is still moving, means in this direction. See, the bag has started moving and coming down, and the bag has reached further in this direction. Okay, the bag has reached from here to, suppose, here. Okay, so the force due to which it is moving, you are applying the counter force over here. You are applying the counter force, but your counter force is you are also applying the torque, but your counter force is not enough. So this is tau 1, suppose, that you are applying by hand, and this is tau 2. Okay, this is tau 2, which is applied by this bag. So tau 2 is greater than tau 1. Okay, so that is why it will rotate. Just like we have F2 is greater than F1, so the net force will be there. Okay, so that is why it is rotating, because the tau 2 was greater. Now in this case, suppose this is tau 3. Okay, you can see that this is the axis of rotation, and this rod has moved from this point to this point, and it will further move in this direction. So it is moving in this direction. Okay, so what is tau here? Will it be positive or negative? Where is the plane? Tau, what is the direction of tau, and will it be positive or negative? So what is this direction? Clockwise or counterclockwise? This direction. Look here, you are moving in this direction. Yes. So theta from reference lines to upward, it is positive. Look here, theta is positive. So this will also be positive, isn't it? So this is what it has moved in this direction, right from here to here. So this is positive, and when it is positive, then torque will come. Torque will be, what is the direction of torque? Torque will be this direction, this point. And what is the negative direction? This. So here negative tau means it is going inside the plane of the paper, and positive tau means it will come out of the plane of the paper, isn't it? So R cross F, this is your R, put your fingers on R and move towards, so this is your R, put your fingers on R and move them towards the force. This is the direction of force. So put your right hand fingers on R and move towards F. Students, can you do it? R and move towards F. Where is your thumb pointing? Where is your thumb pointing?
Towards the torque.
Yes, towards the torque, absolutely. R cross F towards the torque. Is it pointing out of the plane of the paper or inside the plane of the paper?
Out of the plane of
Out
paper.
of the plane of the paper, absolutely. Put your fingers, right hand fingers on R and move curl them towards F, so point will point out. So students, as this bag has come down from this position to this position, you can see that this is your line of action of the force. Line of the action of force is actually, see here, this is the direction of the torque, but the line of the action of force is, this is your gravitational force actually, which is pulling it down. Okay, so this was your line of action. So this diagram little bit, you know, this is the fault that we did. We consider the force here in this direction, but in actual scenario the force is gravitational force and it is acting in this direction. Okay, so this is the line of action of the force, and here the perpendicular distance will be actually this will be your perpendicular distance, not this one. If you are applying the force in this direction, then only this case will be there, but here in actual scenario you can see that this is your gravitational force is always downwards. This is Fg. And what is the line of action of this force? See, this is the line of action of this force. So this is your axis of rotation and this is your line of action of force. So draw a perpendicular from the axis of rotation to the line of action. So that's your perpendicular. So here also it was your perpendicular. Okay, so this is your R perpendicular here, this length. This is your R perpendicular, not this one. Have you got the point, students? Okay, so this length is your R perpendicular. So you can clearly see that this where is the angle? So this axis of rotation, this is your R. This is your R. This is your R. This length is your R length. This R perpendicular. So this is the direction of R and this is your F. Okay, so direction of R and F. So this is angle theta. So where was your angle theta in this case? This is R, this is F. So this was theta. This was theta. Yes. So this is the theta here, and if this is theta, this will also be theta, vertically opposed angles. Okay. Getting it? And this will be, this distance is your R. So this R perpendicular is nothing but R sine theta. Okay. So that's your R sine theta. So Karthik, can you see that this torque is increasing? This is suppose tau 3. So tau 3 is further greater than tau 1, is further greater than tau 2 and further greater than tau 1. Yes, Karthik?
Yes, sir.
So my hand needs to apply more torque here that I cannot apply. Okay. So from the hand in that position actually, you can clearly see that I am unable to, because I am applying the force at the axis of rotation. Where is my hand? So the force that I am applying from my hand is over here, which is at the axis of rotation. So R is 0 here. So the torque that I am applying from my hand is 0. Have you understood? That is why I will not be able to hold this rod in this position. Why? Because why? Because
we are it at axis of rotation.
yes, We are holding it from at the axis of rotation. So if we are applying force at the axis of rotation, R is 0 in this case. So in case of your hand, this tau, this is not the tau 1, means this tau is actually, this is not the tau 1. This tau 1, even if you are writing it at tau 1, the force which your hand is applying, so tau 1 is equals to 0. Why? Because R is equals to 0. So that is why hold this bag on any road, and students, you will never be able to, you know, hold this this bag will keep on moving down in this case. So here means this force is so as this bag is, so the torque is so it is moving due to torque, this bag. So this is rotational motion. Okay students,
Yes, sir.
that's all for today, and see you tomorrow. Thank you so much for being with me. Read from your book the concept, topic 7.7.1. make notes.
Thank you, sir.
Thank you, sir.